Hello, and welcome to the AP Physics C Unit 1 review for kinematics. Today we're going to go over things such as uniformly accelerated motion, projectile motion, scalars, vectors, relative motion, and certain equations that are associated with kinematics. Alright, so starting off, it's important to differentiate between scalars and vectors. Scalars have magnitude only, whereas vectors have magnitude and direction. So for example, distance is a scalar. Same with speed. Whereas their vector counterparts would be position and velocity, right? Distance, if something is 10 meters away, it's 10 meters away. Position, that object with respect to me could be positive 10 meters in front of me or negative 10 meters behind me. Speed is the exact same. Something could be moving at 4 miles per hour, right? Or it could be moving at -4 or +4. That would be velocity. So a really easy way to differentiate between scalars and vectors is to think of a ball that's moving to the left. If we have already established that the up and right directions are the positive y and positive x directions respectively, then this ball moving to the left would have a speed of 3 meters per second, but a velocity of -3 meters per second, which tells me that it's going to the left, is what the negative sign means, at 3 meters per second. So getting more into vectors, when we have vectors that are not in strictly the positive or negative x or y direction, we have to express them in terms of their components, which would be unit vector notation, or their magnitude and direction in order to describe where that vector is going. So for magnitude and direction, for example, if we have this position vector right here, which is at 5 meters per second at an angle theta, that theta turns out to be around 37-ish degrees, then we could say that for magnitude and direction, we could describe this vector as 5 meters at 37 degrees. Now we could also use unit vector notation, which looks a little something like I hat plus j hat. And then for this case, we would describe this vector as 4 I hat plus 3 j hat. Sorry about that. And all that the I hat and j hat means is the I hat means the vector is going 4 in the positive x direction, since 4 is positive, and 3 in the positive y direction. A unit vector is just a vector with magnitude 1, and for I hat it's in the x direction, j hat's in the y direction, and then we multiply them by scalars in order to get them of different lengths. Alright, so now going over the variables in kinematics, we have position, velocity, acceleration, and time. Position is expressed in meters. Velocity is expressed in meters per second. Acceleration is expressed in meters per second squared, and time is simply expressed in seconds. Alright, so now getting into uniformly accelerated motion, there are 3 common equations which we will typically use when we are solving kinematics problems. Our first one is change in position equals v naught t plus 1/2 at squared. Our second one is change in velocity equals at. And our third one is v squared equals v naught squared plus 2a delta x. So these are our 3 common equations that we'll typically use when we're dealing with uniformly accelerated motion problems. And what uniformly accelerated motion means is that a is a constant. And the most normal one that you'll see for acceleration is g. And g is around positive 9.81 meters per second squared. And the reason I say positive is that's just the standard convention that we use in physics, so we don't get our signs mixed up when we have something falling to the earth. So, for example, if we were to plug g into these equations for a ball that's falling towards earth, we would change the positive 1/2 at squared, for example in this first one, to negative 1/2 gt squared. All right, so now moving into position, velocity, and acceleration as functions of time, it's important to know how these three variables will relate to each other when they're expressed as functions. So let's say I have a position function, x of t is equal to 6t cubed. My velocity function, v of t, is going to be equal to x prime of t, or the derivative of position with respect to time. And that's going to be equal to 18t squared. Similarly, when we're moving from velocity to acceleration, acceleration will be the derivative of velocity with respect to time. That's also the same as x double prime of t, and that's going to be, in this case, 36t. So these functions, what's cool about them is that you can jump up and down, as I like to say, or go between position and velocity and acceleration if you simply have one of them. But what's important to know is that if we're moving up the ladder, I guess you could say, so if we're moving from acceleration back to velocity, it's important to know what the initial velocity is, or the velocity at a certain time is, because when you integrate, which would be how you would go back up, there's going to be a plus c, which is added on. And then similarly, if you had velocity and you integrated to get back to position, there would also be a plus c, which you have to add on. Because when you take indefinite integrals, there is a constant that you add on. So if the position, it says at t equals 0, the position is 0, we would know that that constant of integration would be 0. If it said, for example, at t equals 2, the position was 50, we could figure out that the constant of integration, or that plus c, would be plus 2. So what's really nice is that when we know that position, velocity, and acceleration are derivatives and integrals of each other, we can determine certain things by just looking at a graph of the position or velocity or acceleration with respect to time. So let's say we have a graph of velocity versus time. And let's say it looks a little something like this. All right. Now we can say, let's segment this into 3 different little chunks. I can tell you, because of the properties of velocity of a function of velocity with respect to time, right, and how it is the derivative of position and the integral of acceleration, right? Or rather, that acceleration is the derivative of velocity and position is the integral of velocity. I can tell you that the change in position for this entire section of this graph that we see is the integral, right? From this bound on the left, we could just call this A, and then over here, which we could call B. So the integral of velocity from A to B, I can tell you for a fact that it is going to be greater than 0. Similarly, by knowing that acceleration is the derivative of velocity, I can determine that right here, in this first section, acceleration is positive. And also, right here, acceleration in this middle section is equal to 0. And then finally, in this last section, acceleration is less than 0. And I can say all these because I can just look at the slope of this line. Since this line is positive, I know that my acceleration has to be 0, or the derivative of this velocity function at this certain interval is positive. Here, the derivative is 0, so it's because it's a flat line, so the acceleration would be 0. And here, the slope is negative, meaning that acceleration is negative. All right, so now moving into projectile motion. If we have, for example, a ball which is being launched at a speed of 5 meters per second at an angle of 30 degrees from the positive x direction, the horizontal axis, right? We have to do kinematics in 2 dimensions. We have to do kinematics in the y direction and in the x direction in order to determine certain things about the motion of this ball. So let's say we wanted to figure out the total time that this ball was in the air for. Now, we know that this ball will have an initial vertical velocity of 5 times sine 30 degrees. The reason we know this is because this vector right here has a vertical component of the magnitude times sine of the angle, or 5 meters per second times sine of 30. Now, if we wanted to determine when this ball was at its absolute maximum peak, right? So it's getting launched like this, and if we wanted to determine what time it was right here, this would be when the velocity has turned to 0, or the change in velocity is the initial velocity, right? So if we use our kinematics equation, v equals v naught plus at, right? This is the one that's change in velocity equals at. And we know that v final will equal 0, right? Because at the top, there is no more vertical. It's not moving up or down. It's moving horizontal at an instantaneous moment. Then we can determine that negative v naught is going to be our change in velocity, is going to be equal to at, which would mean v naught, we're going to turn this to positive, v naught over a is equal to the time. So this time is going to be the time that it takes for this ball to reach its maximum. And if this ball is going up to a maximum and falling back down, the time between it from its initial launch to its maximum is going to be the exact same time as it from its maximum all the way back to the same level it was launched from. So our time equation is going to be, for this, 5 sine 30, and then g is going to be our acceleration. And then we're going to multiply this all by 2. Since it's going up and then down, that's 2 of these time intervals, I guess you could say. And the reason the negatives cancel out, in case you're wondering, is because technically this would be negative v naught, and this would be negative a, because the acceleration is moving in the opposite direction of the initial velocity. Another thing that is really useful in projectile motion is determining the range, or the total distance that the projectile has moved. So if we again use this ball, which has an initial velocity of 5 meters per second, sorry, and is being launched at an angle of 30 degrees, we can first determine the time, the total time it's in the air. This is assuming that the ball is being launched, right? And then it's going back down to its original height that it started at. So for this, its time would be 5 sine 30 degrees over g. And then all of this multiplied by 2. We could then use this time in the kinematics equation of change in position is going to be equal to v naught t plus 1/2 at squared. Now, Something that's really useful to know is that for projectile motion, the horizontal component of the velocity is never changing. There is no force, there's no acceleration that is acting on that velocity, that component of the velocity. So that is a constant. Knowing that there's no acceleration, this entire part of the equation goes away, and our change in position is just going to be v naught, and I should specify x times time. And this will turn into, if we plug this original equation in, our v naught x is going to be 5 cosine of 30 degrees times 5 sine 30 degrees over g times 2. And that right there is the total range that the ball will travel, or the total distance in the horizontal direction that the ball will travel from its initial position. All right, so the final thing that I want to touch on in this video is relative motion. So relative motion will come up a couple times on the AP exam, and it is when an object is moving, let's say, in the positive x direction, and another object is moving in the negative x direction, let's say. In order to find out what the velocity of this orange object is with respect, or from the view of the yellow object, we take the velocity of the orange one, let's just call this object B, and this object A. We're going to take the velocity of B and subtract it from the velocity of A. And this will give us the velocity of B with respect to A, or the velocity of B from the view of A. That's how I like to think of it. So let's put some numbers to this. If A is moving at an initial velocity of 3 meters per second, and B is moving at an initial velocity of negative 2 meters per second, and their velocities are not changing at all, then at any moment in time, the velocity of B from the view of object A will be negative 2 minus 3, which would equal negative 5 meters per second. So from the perspective of object A, object B will be moving at negative 5 meters per second. And similarly, for object B, right, if we wanted to find the velocity of object A with respect to object B, we would take the velocity of A minus the velocity of B, which would be the same thing as taking 3 minus negative 2, which would give us positive 5 meters per second. So what this means is, from the perspective of object B, object A will be moving past it at 5 meters per second. So you're going to be asked questions that have to deal with relative motion with more than one object or more than one observer in a system. So let's say we have a guy that's standing on a cart. And this guy throws up a ball in the cart. And let's say he's standing on this cart that's moving at 2 meters per second to the right. While this guy's throwing this ball on the cart, this guy is also standing, or there's another guy that's standing on the ground. And he's watching this. So from this scenario, what is the velocity of the ball from the perspective of person B? Let's label this person person A and person B. So the guy, for person B, he will see this ball moving at what he sees as 2 meters per second. And this is because while this ball, which is being thrown directly upwards, has no horizontal velocity from the perspective of the guy at position A, right? So this guy's will observe the ball having a velocity or a horizontal velocity of 0 meters per second, this guy standing on the ground will have the cart. We'll see the cart moving. And the guy standing on the cart is throwing the ball. Therefore, the ball is also moving at the same speed of the cart. So this guy will see the ball moving at 2 meters per second in the horizontal direction. All right, guys, thank you so much for watching. This was my first video on this channel, so please comment and let me know if there's anything that I can do to improve, any way that I can help explain things better, and if you have any questions about any of the things that I described in the video, please let me know in the comments below. I should be making a Unit 2 video, and the rest of the units for AP Physics C Mechanics at least, so that's Units 1 through 7 of the AP Physics C curriculum. So stay tuned to see those. And the AP test is coming up in the next 11 days. On May 14th this year of 2025, we will have the AP Physics C Mechanics test. So I should be getting all of those videos out before that time. So if you're looking to watch them all, then, hopefully this could help you. Anyways, thank you guys for watching, and I will see you in the next video.